Good morning, everyone. If we can please be seated. I hope you had an enjoyable night last night. We're on the last day of the Congress, and we're very excited this morning to bring to you the leaders of IFAR. They will explain to us what that means, but it's the union of the various research organizations. And as you heard from Anders Blum on the first day, when ICAS was created, was predominantly the leaders of the research organizations that brought us together. So the format today is we have 5 speakers, and I will introduce them to you, so we don't have to go up and down all the time. Then they will come up here, they will give the presentation, and then we have a good 25 or so minutes to ask some questions. And at the very end, we need a few minutes because IFAR gives an award every year to one of their employees, and we're going to give some time for that one. So I'm going to introduce the speakers in the order that will appear. So Dr. IbrahimYimer will be the first one. He's the Vice President for the National Research Council of Canada. He is the Vice President of Transportation and Manufacturing Division. And his education started in Addis Ababa in Ethiopia as a chemical engineer. And then he received a master's and a PhD also in chemical engineering from Queen's University in Kingston, Ohio. Our second speaker, Markus Fischer, he is the divisional board member for aeronautics for DLR, the German Aerospace Center. His degrees are from the Technical University of Braunschweig. And he is right now the DLR Director of Aeronautics Program and Divisional Board member. Our third speaker will be Bruno Sainjon, Chairman and CEO of ONERA since May of 2014. He also has served in many, many positions, including Chairman of AREA. Right after that, Peter Krus is going to join us as representative of the Swedish Aerospace Research Network. Of course, he's well known to this community here. He's a professor from Linköping. And our last presenter will be Dr. Watanabe, who is from JAXA. He's the Director of Management and Integration at JAXA. He holds a doctorate degree from the Tokyo University. So, Ibrahim, I will ask you to join us up here. I think we're up for a very informative set of presentations. And please hold questions for the end.
Thank you, Dimitri.
Thank you.
Thank you. Okay, good morning, everyone. It's a real pleasure to be back here once again, here in ICAS in person. This is a great collaboration that we have between IFAR and ICAS, where we come once every year in front of you and just tell you what we've done as an IFAR organization. So before we just launch into the lecture, I thought maybe I'll just give you a quick primer. It's a bit of an update, actually, about IFAR. IFAR, for those of you who does not know IFAR, it stands for International Forum for Aviation Research. We're a group of government-funded aeronautical research organizations from about 26 countries in 6 continents. All in all, we represent about 35,000 researchers in 6 continents. And these are the 4 core values of IFAR. I mean, we had a session yesterday morning. We always have a session in the ICAS technical program. And I think my colleague, Kristen Eschman, gave a very good primer of IFAR in that particular session. So I'll just provide just a quick update on those 4 areas. First of all, we meet every year, all the heads of the principals of this organization in a summit in one of our countries, primarily to do networking and usually focus on a particular thematic areas, and we try to coalesce or converge into the most important problems of the aeronautical industry, the aeronautical community as time goes by. But we also bring in our researchers for information exchange for sure, but what makes us slightly different here is we get them to do projects together. We get them to do activities together. And that's also a forum where they exchange information, their results, hopefully leading to or is leading to into a collaborative activity between our organizations. Much like you, as in ICAS, we care about bringing young talent into the community, keeping them engaged, keeping them connected, developing very collaborative roots or relationships, if you will, and mentoring them, etc. So human resources development is the other. And finally, the external partnerships. We partner with our colleagues, such as ICAS, and this year we have added another name, which is the ICAO. So if I go just one by one, obviously we had a very good summit in person, or it's a hybrid actually, in one of our host countries, Warsaw in this case, the Institute of Aviation, ILOT, while they were celebrating their 95th anniversary. And not surprisingly, we've been, of course, talking about sustainable aviation. Here, there you see we got about 17 of principals, the principals of the organizations were there. And you can see the picture of one of our speakers, Ligia from NLR, talking about the area's vision study. And the real key takeaway there is if we really are serious about meeting the goals, the sustainability goals, international collaboration is absolutely essential. Here you see probably a familiar face here, Prajwal, who is also quite familiar here in ICAS. We encourage them to really put an X-Challenge program that you see, and some of the results of this is actually presented in the technical session of the IFAR. As I said, this year it took place yesterday. Really, as I said, the goal here is to provide a very good platform for youngsters, young career professionals to get a very strong international network. In terms of connecting our technical folks, we do have 10 technical working groups. You'll see a list of the areas. These are the examples. There are about 7, but we do have 10 standing working groups. And back about a few months ago, we had a special meeting out in Canada, in Montreal and Ottawa, in collaboration with some of the ICAO technical folks. And you'll see some of the pictures where the group discussion took place, particularly on the subject of hybrid air mobility. It's an area of importance for ICAO, of course, and it was great to be able to really start up that relationship in this spring. Yeah, just speaking of ICAO, we found actually a very good synergy between what IFAR as an organization is able to provide in terms of very unbiased scientific information, basically together from all these nations, 26 countries or the member organizations. They thought that that's a very, very useful document, an international in a sense, that they can use it to bring into as an input to their standard or rule-making process. And as you can see in some of the pictures, as I mentioned, the topic that we chose in order to do, these are 2 large organizations, by the way, and developing a relationship always takes time. And we chose this urban air mobility as a pathfinder project, if you will. And we get about 80 of our researchers from a handful of the member organizations. I think we are now, I don't know, around 10 or 12 organizations contributing towards developing a scientific assessment on a range of both technical, societal, as well as operational issues associated with getting the urban air mobility industry up in the air. And the photograph that you see there is just some of the samples of what we were able to do this past spring. Now, we signed an MOU with ICAO, and you'll see the Secretary General Salazar It was a hybrid arrangement, as is the case in most of our events these days. And we have also the opportunity to have a session with the with members of the council, the ICAO council in the chamber, including the president of the ICAO council. So we hope to see this is a very good collaboration that we're launching here, and will be hopefully the start of a long-term and fruitful relationship. By the way, that technical working group is working really hard, trying to provide an output. In the first output that we hope to see is the first quarter of next year. This may even line up very nicely. Talking to Dimitri, you're now doing some specialist meetings in between the conference years. This may be a very interesting opportunity to be able to even expand or develop on the interaction we have between the two organizations. So this is just a summary. What I will do then, if I can, is introduce the topic of the day. We'll start off with a video from DLR. Markus Fischer was not able to be here in person, but he has given a very good presentation from a video, perfectly timed to 9 minutes. We'll start off with that, and we'll go with Bruno from Onera, and that's Dimitri Said and SARC. SARC is now our Swedish organization that sits in the IFAR group. And then I'll come back for NRC, just talking about electrification, and wrap up with JAXA. So with that, maybe I will get the video rolling.
Ladies and gentlemen, my name is Dr. Markus Fischer. I'm working for the German Aerospace Center, the DLR, as Divisional Board Member for Aeronautics. The title of my presentation is Application and Measurement of Sustainable Aviation Fuels in Real Environment. The nice graphic which you see here comes from Lee et al. And shows the various contributors to climate forcing by aviation. Sketched on the upper left is a contribution by accumulated CO2 and water vapor. There are other contributors grouped as non-CO2 effects. The far by largest effect is the cirrus formation caused by contrails in atmospheric regions of low temperature and supersaturated air. See this in the middle of the picture and explanatory box at the bottom. Analysis shows that contrails have the largest contribution to effective radiative forcing measured in milliwatt per square meter. Study shows that 2/3 of the climate impact from aviation over the last 80 years comes from non-CO2 effects. This picture comes also from Lee et al. Explains by means of the global warming potential the large contribution by non-CO2 effects, shown here as temporarily accumulated over 20, 50, and 100 years. The non-CO2 effects are important even on long time scales. Referred to the CO2 effect, the influence by non-CO2 effects lessen over longer time periods. However, it remains in the same order as CO2. Thus, focus of our research must consider both effects, CO2 and non-CO2. In response to the European Green Deal 2050, DLR published recently a strategy paper titled as A Visionary Statement Towards Zero Emission Aviation. One of the major results of this strategy are 4 research activity domains showing the key technologies and its application as enablers to achieve the Green Deal target. Top left, you see the low emission propulsion system and technologies, including the use of all types of sustainable energy carriers. Top right, the counterpart to it, the energy efficient aircraft. Bottom left, the emission-reduced air transportation system with the option of a climate-friendly routing of aircraft and the determination of the atmospheric climate impact of aviation. Finally, on the bottom right, digitalization as a backbone domain for all the others. In doing so, DLR's research approach is systemic and technology open, studying the benefits and impacts of each technology in the entire air transportation system. If we firstly consider the CO2 effects on climate and the corresponding mitigation measures, then the recent DLR aeronautics strategy in support of the European Green Deal provide answers to it. The graphic shows the CO2 emissions by aviation until the mid of this century. The assumptions behind are listed at the bottom. The black upper curve shows the emission for the predicted air traffic growth when no measures are taken. The purple curve below shows the mitigation potential when technologies from the energy-efficient aircraft domain are applied, such as new configurations, lightweight systems design, and a 50% reduction of own energy consumption. Also, the digitalization domain will enable or even amplify many design steps in this context. Please note, the considered propulsion systems are still of conventional or evolutionary nature. The blue curve refines the purple scenario by using sustainable produced kerosene for all aircraft classes. Finally, the green curve shows then the best case scenario by using sustainable produced kerosene for long-haul flights and hydrogen for regional short and medium-haul flights. The overall result will be a marginal threshold of only approximately 70% of carbon dioxide emissions compared to 2020. If we now consider the non-CO2 effects, and here the by far largest effect, the cirrus formation caused by contrails in atmospheric regions of low temperature and supersaturated air, research findings show that roughly only 10% of all worldwide flights are responsible for 80% of this effect. See the picture for this at the upper left, based on recent material by Theo, Schumann, Vogt et al. A highly effective mitigation measure is to circumnavigate those regions in the upper atmosphere by derouting the aircraft to avoid the cirrus formation. Studies by Mattes et al. See the picture at the lower left, that the expenses in terms of additional operational costs pay back with a big lever arm of reduced climate impact. A very efficient measure in terms of benefit cost analysis. This slide shows DLR's process chain to investigate the use and the impact of sustainable fuels, in particular equivalents to kerosene. It starts on the left side of the picture with a simulation platform to compose and analyze fuels according to ASTM standard. The complementary combustion research takes place analyzing and controlling the combustion process and developing the necessary technologies to minimize the resulting emissions. In the next step, the applicability of these fuels and its environmental impact is measured on ground and in flight under real conditions. DLR uses a Falcon flight test aircraft equipped with various measurement techniques to capture and analyze the resulting emissions in near-field conditions following the emitting aircraft. The achieved data will be analyzed and used to refine and further develop atmospheric and climate models. Likewise, in terms of a cause and effect analysis, the data is essential for the refinement of the design of future aircraft concepts. And the result on aircraft level will be fed back to the initial fuel design so that a closed design and assessment loop is present. Since 2014, DLR plus partners have systematically studied the use and impact of bio-based kerosene in the 3 ICLIF campaigns under real conditions. The first campaign in 2014 with the outlined partners showed as a major result that 50% blend with HEFA fuel, which is hydroprocessed esters and fatty acids, reduces the soot by roughly 50%. On top, the second campaign in 2018 showed that this 50% soot reduction results in a reduction of ice particles in the same order. In the recent ECLIF campaign, which Airbus has flown with Rolls-Royce, Neste and DLR, it could be shown that an A350 XWB-900 with Rolls-Royce engine was flown in both engines with 100% IFAR fuel. A big success. The same process chain as shown in the one former slides for equivalence to kerosene is applied for the use of H2. From left to right, you see the development of technologies and methods for H2 direct burn in aero engines. This includes the combustion process as well as the impact of H2 on turbofan components. The right side shows the research of DLR and partners to calculate and measure the micro-physical properties of hydrogen contrails in the upper atmosphere. This will contribute to a better understanding of the formation of contrails resulting from hydrogen propulsion. Of course, the impact of released water by fuel cell operation is also part of these studies, but not shown in this presentation. And with this slide, I will finish my presentation and thank you for listening.
Okay, that's right. Good morning, everybody. 12 minutes, 13 slides, being one of 5 RTO's presentations, quite a challenge. So I will start quickly with a first slide reminding you the global context in which we react to reach this climate challenge, which has been put in front of us a little more than 3 years ago. And of course, also the profession has started strongly to adapt to answer this need and challenges. This slide reminds you also that we are not starting from nowhere and that for decades we have worked for the reduction of all kinds of environmental problems, be there noise or be there the reduction of the consumption of kerosene. Of course, it's important to remind that the efforts and the results which were obtained in the reduction of kerosene were mostly based on economical options, reducing the cost for the companies. And now the driver has changed. The driver is clearly the climate impact of aviation. That's what we are working on. We think that we RTOs, we have the duty to light the future of aviation. Of course, it's one of our missions since the beginning of each of us. And for each of us in our country, we have mainly 2 roles. One is as a public entity, public research entity. We provide key and discutable scientific data, technical data to our government services. And we are also a second as important role, which makes us sort of a bridge between the fundamental research, mostly made by academics, that we reach up and transfer to the more applied research, which is, of course, needed by industry. This we do in each of our country. And of course, we do that as a bunch and collectivities like, of course, IFAR, for which we are speaking today. And it was also mentioned by Ibrahim earlier when he spoke about AREA, which is, let's say, the European sister of IFAR. AREA produced about 18 months ago its vision study about what could be the future of aviation in different scenarios in 2050. You've seen this slide so many times that I will skip it. We are all trying to drive this curve back. Maybe just one message here is to remember also that all the efforts and all the results will not be necessarily provided by the aviation community. And for example, green hydrogen will probably be provided by specialists of that because the need for green hydrogen far encompasses the needs of the single aviation. So we have to reduce emissions, and what kind of emissions? I will quote again Markus saying CO2, but not only CO2. We will think about that. You have just here the reminder of the real contribution of the aviation contribution in terms of CO2 emissions. How can we do that? I will try to illustrate that. We are working on 4 major axes: low carbon fuel, energetic efficiency, aircraft electrification, and operation. I will just select one example amongst many others in each of the 3 first axes. Starting with low carbon fuels, Markus has spoke about SAF, so I will speak a little more about hydrogen. Once again, reminding that not all will come from aviation community, but of course, aviation community have to face very interesting challenges in terms of technology, in terms of research, but also in terms of science to answer the hydrogen needs. And it's important also to remember that hydrogen will not be the answer to all the problems of all the segments of aviation. It will answer a part of it. One of the major phases which are listed there that we will have to face will be the tank volumes, will be the cryogenic aspects, or the injection and combustion problems that it brings. And you can see on the bottom right of the curve a big calculation example which has been made by honorary teams with a new injection chamber concept, including 4 injectors for hydrogen combustion. On the second topic, improving efficiency, improving propulsion efficiency, I've chosen to illustrate it with something called boundary layer ingestion, in something which is very well known in some fields like low speed, for example, but other fields have to be investigated. As you can see on this slide, you can see quite different kinds of designs for the planes, and it's certainly one interest of this BLI concept is that it can adapt almost to all kind of configuration and all kind of propulsion. Third axe with 2 slides in terms of electrification. The first one is to introduce or remind what's probably the most important European effort under the funding of the Commission. It's a project called IMOTEP. You see the figures on the bottom right. 33 teams involved, from academics to big industry, 9 European countries, 2 international partners under the coordination from Hornera. You can see that it's dedicated to 2 kind of segments, the regional transport and the small and medium aviation. And you can also see that we are working on, let's say, conservative configuration, going to far more innovative ones. And if you see the one in the bottom left of those 4 cases, it's a second slide, which is about a project called Dragon that we are leading. Dragon is made under the funding of Clean Sky. Clean Sky selected 3 projects for electrification. We were quite happy to see that the Oneras concept was the one they had chosen to present on the last budget exhibition. And as you can see on the slide, it's a mix between things which are already known and sometimes applied, like, for example, non-circular fuselage, you know about Airbus A380 using it, for example, and something quite new, totally new, like the distributed electric architecture you can see there on the slide. So let's go back to the impact effect and the CO2 emissions. Markus spoke about that. He remembered that CO2 effects are less than 50%. We have to work on CO2 yet, of course. One of the reasons being that, and it's illustrated on it wants to be illustrated at least on the right curve there, it lingers longer in the atmosphere. So that's the reason why we have to fight against that. And the other aspects, water, contrails, NOxes, the problem is that there are a lot of uncertainties yet about what they do and about their effect on climate impact, which is once again the driver. So we have to work strongly on that. And that's the reason why in France, DGIC has decided to launch a very strong study on that, bringing together people from aeronautics family, specialists, for example, yes, that's here. Mixing people from the aviation community with experts from climate sciences, and we have been given the responsibility of conducting these studies. Whatever the field, whatever the axis we will select, nobody will accept any compromise on safety, of course. And that's, again, a role we think is interesting for us RTOs, and that's one of the reasons why we have been approached, or we have approached individually, together, international entities which are in charge of the problems of security. That's the reason why, and Ibrahim showed it, we have made this partnership with ICAO. That's the reason why in Europe we are in bunch or individually working closer with EASA now. Modelization, digitalization will have an important thing in that, because we will not test everything experimentally, even if, of course, we will have to progress on that also. So we are all developing, with often the help of our governments, or tools, or means, or calculation, because we already have a large experience in that. Onerous codes are used by industry for sometimes decades, but we have also to develop, to improve them in order to answer these new challenges. And as a conclusion, I will say that, as I said at the beginning, we have a new challenge. We have strongly begun to prepare the answers to that and began to work on that. We know that we will have to evolve, to bring new things in our practices, like digitalization, like electrification matters, like climatic sciences, of course. Once again, we think that we RTOs are able to bring something more, maybe because we are acting in a less competitive world than the world of industry. This brings up the possibility to more international cooperation. That's the reason why for ONERA we have been involved since the beginning in IFAR, and we will keep on being strongly involved in IFAR. I thank you for your listening, and I now give the floor to my friend Peter Krus, from SARC in Sweden. Thank you.
Well, good morning. I'm delighted to be here on behalf of SARC. SARC is the Swedish Aerospace Research Center, and it's a distributed center between the major universities in Sweden. And we are a new member of IFAR. I'm also delighted to see that IFAR, the objective of IFAR, is very much in line with what SARC is. The intention of SARC was to let's see. How's this? No, sorry. Okay. The intention of SARC is to promote PhD development. We have a research school. It's also about internationalization for the people in the network. And it's also about collaborative projects. And I think all of these things are very much in line with IFAR. One of the things we are looking at is sustainable aviation. And I think it's important to have an independent body like SARC to do this kind of investigation. And because there are so many different views on this kind of technologies, so it can be hard to navigate between them. We have made this study on sustainable aviation. We looked at both hydrogen and electric power plants. And I will here look a little bit more on electric and in particular hydrogen hybrid aircraft. And there are, in addition to technical feasibility, you also have to look at commercial feasibility, regulatory compatibility, and also, of course, climate impact reduction, and not least also societal impact. One thing that we found very useful is to look at the cost-benefit factor. What is the maximum range of an electric aircraft? Well, you can have zero payload and everything being batteries or hydrogen. But there is also a level where it doesn't make sense. And in this graph, the lower part is in an area where you have more fuel, battery than you have payload. And that, in that case, the aircraft will be the weight will increase very much with range for a given payload. So it doesn't make any sense, really. So that means that in our case, we have 3 curves there, counting for an 8% increase of battery specific energy. And this is a pure battery electric aircraft then. And that means that for present state technology, we are less than 500 kilometers theoretical range. And from that, we have to subtract any reserves. But then we can also look at the hydrogen fuel cell combination. And with a pressurized storage, which is I think the more logistically easy alternative to cryogenic, we could still get up to more than 200 kilometers and still have reasonable payload fraction. I could say that here we have used quite high LODs of 20, 90% efficiency of the propulsion system, and a 40% fraction for the rest of the aircraft, which is not fuel or payload. So this is a very sketchy way of doing it, but I think it says a lot, and you don't have to go much further to realize what the potential and limitations of the different technologies are. However, it's also interesting to see what is the potential of these ranges. And if you look at what we have in the US here, we can see that only if you can fly 500 kilometers, it's only corresponds to 5% of consumed fuel. This is flights in and out from the US. So it has a very limited climate impact in the foreseeable future. Looking at Sweden, we have a population density as this. Most people live in the south. And if you look at the number of flights from different places, it looks something like this. So about 520 kilometers covers about 50% of all flights. We should also look at the driving time to the airport, and this is a heat map of how much time it takes to go to the nearest airport. The medium blue there is 2 hours, and the dark blue is the darker it is, the shorter it is. This is for car only, but if you add train transportation, that will probably not improve it much, because you need much more. You need more margins, and the trains don't go that often. you can also look at individual flights here, and you see that for the longest ones are long ones are Stockholm to the very north, although there are not very many flights. If you look at the distribution of flights, we can see that more than 75% of all flights are covered if you go up to 600 kilometers. So if you look at also societal aspects, I think it's important to see that low-cost aviation could be is of benefit for sparsely populated areas with poor infrastructure. And you can argue that you could, instead of investing in very expensive infrastructure, you could actually subsidize some of these transportation needs. And this can be used to compensate for increased economic segregation of regions, since it otherwise will mostly benefit already economically strong regions. I would just like to show a quick more detailed analysis of electric hybrid aircraft, where we use the system simulation and simulation-based optimization to optimize the different components. In this case, we have electric motors, we have batteries, and a fuel cell. And we fly a mission of 500 kilometers and then 1,000 kilometers. So we use present-day technology, 200 watt-hour per kilogram. And the limiting factor also, which I think some people tend to forget, is the specific power of batteries. You cannot go up to more than 3C, or you cannot discharge a battery probably in less than 20 minutes before you deteriorate the life of the battery. Short durations, you can go up to 10C or more. Another limiting factor is fuel cells. It's hard to say for me what the specific power is, but if you say it's 1 kilowatt per kilogram, that's approximately what a piston engine was before the Second World War. So we are looking at a DC-3 or something. So it's a limitation on speed. A pressurized hydrogen storage of 700 bars, we have a fuel fraction of just 6%. So only 6% of the weight of the tank is actually hydrogen. Nevertheless, you have a specific energy that is several times higher than for batteries. So we optimize here for battery size, hydrogen volume, fuel cell area, and max current. And you can see here that the batteries are automatically adjust to take care of the takeoff part. There is some excess power available from the fuel cell that can augment the takeoff and climb part. Because there is a balance in the fuel cell between weight and power and efficiency. So if you want to have a low weight of the battery of the fuel cell, you will sacrifice some of your efficiency. We looked at two cases, 500 and 1,000 kilometers. I will just skip to the result, really. For the 500 kilometer range, this is theoretical range, no reserves. We can have 2,300 kilos in payload mass. If we go to 1,000 kilometers, we're down to 1,900 with present-day technology. If we go further and double the specific energy of batteries and the specific power of fuel cells, we get up to 2,500 kilos. We also see that the fuel cell, of course, fuel cell mass goes down dramatically from almost 1,000 kilos to less than 500 kilos. And that could be used instead to increase the speed of the aircraft. In this case, it's only 360 kilometers. So if you look at conclusions here, we have a technical feasibility for better electric aircraft, I think the technical feasibility is only for very short theoretical ranges, less than 500 kilometers. Commercial feasibility is for niche applications, for instance, island hopping, where it's hard to where there's no real competition from roads. The climate impact, however, is quite small. Electric hybrid aircraft, battery plus hydrogen, I think have a significant potential in regional transport. We can have theoretical ranges less than 250 kilometers with pressurized tanks. And the limitation is speed due to the specific power of fuel cells will likely be lifted if we go up with the development. We're still early in the development cycle of fuel cells, I believe. So the commercial feasibility is there for commuter aircraft. The climate impact could potentially be like something like 30-35% if you look at flights inside and out from the US. In Sweden, it would be cover most of the domestic flights, actually. Societal impact is that low cost of regional aviation can be beneficial for sparsely populated areas with little infrastructure. Then we have the operations and regulations, and allowing for a single pilot operation could have a large impact on cost of operations. We need more efficient passenger processing for short flights, because otherwise that becomes unacceptable long. Reserves are very hard to negotiate. For instance, you need 1 or 2 alternative airports. You need to be able to go around a 30 minutes loitering. So that is probably have to stay. We also need to have charging and refueling infrastructure, also an alternative airports probably to be able to go away from there. And not least, we also need to have in place a better, more precise regulations for electrical environments, like to be able to deal with electric charging at airports. Okay, thank you.
The theme of electrification, I'll see if I can add just a couple more points. Most of our results are very similar. I'll just talk about electrification, particularly on batteries and high voltage cables, and probably try to highlight the importance of facilities and demonstrators. So first, a little disclaimer. Electrification is just only one potential solution. But I do argue that even though it doesn't take us all the way there, we need to decarbonize the whole the aircraft in all sizes, and it's still very important that we still talk about it and still drive the technology. But the others are also obviously very important. So you've seen this chart, and I won't dwell too much on it. I just simply added on the left margin the megawatt power, just trying to focus a little bit more on the electrical side of it. So you can see we will be able to touch only the commuter class and the regional class. And another point worth making here is, besides trying to decarbonize all the aircraft classes, the smaller aircraft is really an excellent platform to be able to mature technologies, to be able to learn a lot at a lower scale before we scale them up to a hybrid electric or a larger scale. So I'm putting here a chart that's very familiar. Sometimes you put passengers or cost on the vertical side, again, concentrating on mainly on electrification. You'll see the wattage there. So we talked about the energy density. I think Peter talked about the energy density of batteries, etc. Just to give us a reference, you'll have the jet fuel current kerosene energy density, which is about 1.2 kilowatt per kilogram, but you apply essentially the efficiency of a gas turbine, the usable energy is in the order of 6,000 watt-hour per kilogram. Because we have to fly, and not only on the road, we not only care about the energy density of the fuel, but we care about the power density of the power plant itself. So typically, again, as a reference, smaller gas turbines will give you in the order of 2 to 5 kilowatt per kilogram. And if you're looking at like modern turbofan engines, it's in the order of 10 to 15 kilowatt per kilogram. So where are batteries? I mean, what I'm trying to portray here is what is the space, the design space, and how far are batteries of today, and how far can we extend them? So you can see, theoretically, I'm a chemical engineer, as Dimitri introduced me. Maybe we can talk a little bit about the current chemistry here. At the cell level, you can actually theoretically draw out about 3,600 watt-hour per kilogram. But obviously, as you become more practical, you try to package it. Even at the theoretical limit at the pack level is in the order of 8 watt-hour per kilogram. So you're already 4 times reduced. Then, if we look at just the state of the art of battery technology today, again at a pack level, where we are is typically in the order of 270 watt-hour per kilogram. And if you decide to go out and buy a battery today, 99% probability is designed only for automotive application, then you are way out in the corner there, which is around 170 watt per kilogram. Now, a modern turbofan engine, if you take a 300-passenger aircraft, will require approximately 25, 50 megawatt per engine. So it's fairly way out there. So when we say electrification doesn't take us, it's way out of the theoretical battery chemistry, what the battery chemistry can provide. So clearly it's out of range. But look at the UAM target. The UAM target is in the order, this is about sub-megawatt power, and it's within the theoretical package limit. So there is still a little space to be optimized. Now, obviously, we've got hybrids. Hybrids will give us bridges in between that, and hopefully with sustainable aviation fuels. And if you look at the current examples of that we see, most of the demonstrators that we've been flying are very much still in the corner. So the message out here is the battery technology has a huge theoretical capacity, but the practical capacity is way down. And we're really experimenting with a battery that's really designed primarily for automotive application. Yeah, here is essentially a small video that shows you at NRC, in my own organization, we are also experimenting a little bit. We're learning by doing, if you will, using a general aviation aircraft. It's a similar Cessna 337, very much like what Ampere did a few years ago. Here we took the back engine and replaced it with 160 kilowatt, battery-driven drive, essentially. And we just took this up in the air this last winter. You can see in the background a good Canadian winter there. But so there is a lot of learning to be had, is the point. First, when it comes to, I think this was mentioned here, when it comes to specific regulation, there's essentially nothing by way of regulation that would allow you, that would actually state battery design, or even the overall integration of the power system. So we had to bring in the regulators with us. We've been doing essentially learning together with the regulators. And that's, again, the advantage of an RTO. A very important thing that we've learned is the thermal management side of the batteries. It's absolutely critical in the system design, but also on the operation of it. Essentially, when you pack these batteries, if you have fire in one of the packs, you will have to make sure that it has to be contained, and not only separating the thermal release from each of the packs, but also even the exhaust that comes from the batteries during a thermal initiation. It has to be really evacuated directly from the cabin, and its very toxic fumes should not be able to come back in there. So a very critical lesson there. Supplier selection, which is just, this is the logistics side of it, is also very much unknown, really. If you order a battery now, you cannot even ship the battery alone. It's considered as a dangerous good. So you have to kind of buy it with the car, for example, or somehow package or integrated. And also you're getting it from suppliers with very little knowledge in terms of reliability and points of failure. So we have to do all of that together. The other interesting thing we've done is, I think, different from what Ampere did. In our experience, we went with a higher voltage. Basically, it reduces the current requirement, and hence you'll have a lower weight on the cables. But when you do higher voltage, it also at altitude, it also introduces other risks and challenges, and we've learned quite a bit on it. The other element is the verification and validation of the risk analysis, the system verification that you have to do at the system level. These are fairly complex systems. You're bringing in not only the electric motor, the converter, the inverters, etc., and being able to identify the criticality of the subsystems is very difficult. So you have to start right from the beginning, an overarching verification of or validation of the process itself. The cockpit, the control itself, you have both, particularly on the hybrid configuration, you'll have both propulsive systems, the normal IC engine in this case, but also the electric system. So it doesn't exist, and we have to make it happen, essentially make it custom build it. Finally, this was also already mentioned, if you look at battery-powered electric aircraft certification, the global harmonization, we haven't arrived there yet, and there's still some work to be done. A particular example, if you will, is the Pipistrel trainer, which is really certified in Europe 2 years ago. When it comes to North America, I think that's still in the process. So enough about the smaller scale. What takes us now from a smaller scale demonstrator is to this larger hybrid, and these are some of the examples that are out there that we look forward to learning from, understanding from now at a higher power rate. I've given here just a couple of examples on the on the European side. And the Dornier 228, we're replacing one engine by a 600 kilowatt, and you've seen this the middle one before, even in yesterday's talk here, a sub 340 now replacing one of them with 1 megawatt. On the Canadian side, we're also looking at a similar demonstrator, taking a Dash 8 100, which is a de Havilland, Canada, and Pratt & Whitney Canada collaboration, where we're now replacing one engine by 2 megawatts. So these are actually happening in the next few years, in the near term, and we'll be learning quite a lot from these demonstrators as we upgrade the power requirements, the electrical power requirements. Now, I just want to mention just a couple more points. One is about this battery design. I indicated that current day batteries are really optimized mainly for automotive application. So if you start again from a theoretical specific energy, let's say if you start from really aviation-specific application, you will have fluoride carbon lithium, you will have 3,600 watt-hour, but now as you come down, an actual pack-specific energy, there is 4 to 6 times reduction. That's something I think we can, as an aviation, on the aviation side, really put more focus and be able to optimize even further. So further R&D is required for aviation-specific needs. The other element is, again, high voltage. the power industry handles, kilovolts or hundreds of kilovolts. But if you want to take even 1 kilovolt up at an altitude, that's completely uncharted territory, really, mainly because of these altitude effects. Just to illustrate that a little bit, you will see on the right-hand side the so-called Paschen law. As you go up in altitude, what you'll be able to carry in terms of voltage essentially goes down, again, due to arcing and voltage breakdown effects. So what does that mean is, if we want to fly at an altitude and we want to really reduce the size of the cables, etc., and really optimize the voltage, then we've got a design barrier that we need to really deal with. Here we just showed about one possibility of even trying to expand that a little bit further. You've seen if you can use the gap and the connectors, that will move the design space to the right a little bit and allow us to carry even higher voltages than we would be risking. So it's just a very key point. I think yesterday it was also mentioned here. It's not a really sexy part of actually the design, but the cables can be an area of highly, research whether it's advanced materials on the insulation side or light weighting itself, but also on better conductivity. So one last point here is about test facilities. Now, we are RTOs, and we tend to own these large infrastructures where we do compliance by testing. I don't think we'll be at a point where we will be, we will have to certify these products, and they won't be certified by analysis, needless to say. So all of us are looking at these, essentially building a parallel facilities that would eventually become the compliance capability as we bring in all these new technologies. This could be a flying platform, this could be a static platform. I think the point to make here is they're going to be very more specialized and complex, and as a result, they will cost a lot, but also they're going to be low utilization. So here is again IFAR, an organization that of RTOs, where we discuss in our IFAR meetings what are we planning in terms of upgrading, in terms of facilities for better, complementarity and maximizing utilization, such that we can accelerate essentially, putting these products, certified products, without compromising safety. So in summary, what I'm trying to say here is, electrification is part of the solution, but we should still keep an eye on it. That's not something, it's 27% if you look at the two classes of the aircraft, but that 27% is also very important. And I think the batteries are optimized mainly for surface transportation, and I think there is some work as a community we can do to even eke out what's available from a theoretical energy density perspective. High voltage cables, again, is very little research in that area. From a material side, there is a lot that can be done. And cooperation in general is very much needed if we want to really decarbonize the full sector and harmonize the regulation of the certifications that we all need before we put this thing up. So at that point, I think I will stop, and I'll let the final speaker from JAXA.
Good morning, everyone. I'm Yasushi Watanabe from JAXA. So today, I would like to introduce the electrification of aircraft that JAXA is working on. So in the first part of my presentation, I would like to analyze what challenges we face in realizing global goals. And in this context, I would like to talk about what goals we should set for technological development. And in the second part, I'd like to introduce JAXA's goals regarding aircraft electrification technology. So, as you know, this is a goal of achieving zero emission by 2050, as outlined in ATAG's Waypoint 2050. There are 4 components to achieving this goal. Improved aircraft performance, which includes current and new technologies. Ground infrastructure and operations, replacement to SAF, including hydrogen and carbon offsets. So today's topic, electrification of aircraft, is included in the application of new technologies. Okay. So this figure shows the contribution of 4 elements. There are several patterns in the breakdown of contributions. For example, left side shows ATAG's scenario 0 with a high contribution of carbon offsets. And right-hand side shows the pattern shown by IATA, which is highly dependent on SAF. So JAXA refers to ATAG's scenario 3, which has the highest dependence on technology development. So, based on ATAG's scenario 3, I would like to clarify some important points when considering the goal of technology development. Okay, so the first, let us consider the SAF replacement. This chart shows CO2 reduction versus the replacement rate to SAF. The reduction target shown in red line here are values estimated by JAXA based on ATAG's scenario 3. And the current status of SAF replacement is extremely low, as shown in the IATA report, and it is estimated that 1,000 times more production capability would be required to achieve 100% replacement. And even if the SAF production issues are solved, there is another important point to consider. That is CO2 reduction rate during life cycle of SAF. And the CO2 reduction rate of an ideal SAF is 1.0. This would achieve the goal by replacing about 90%. However, the current reduction rate of biofuels is set to be about 0.65, and even for CO2-free hydrogen, it is 0.75. So therefore, I think it is important to improve the quality of SAF or reduce the dependence of SAF replacement. So increasing dependence on technology, for example, making aircraft more fuel efficient would be very effective because we can set a reduction target to lower value. So this is why JAXA is considering ATAG scenario 3 as a basis. Okay. So now that you understand the importance of improving fuel efficiency, we would like to consider the technology. This is a conceptual drawing of ultimate electrified aircraft envisioned by JAXA. It is equipped with a propulsion system called Series Hybrid, and it applies a power system that combines hydrogen fuel, gas turbine, and batteries. It also applies a distributed fan system with superconducting motors to improve efficiency. So the problem is the timing of its realization. Of course, we cannot show its feasibility with the current technology. So JAXA has set the date of realization for 2050 or later. So it is important to develop technology for such an ultimate goal, but it will not contribute to the realization of the global goal. So what we should do, so as one answer to this question, we believe that several steps of technological development should be done. So in other words, agile development is required. So, but there is one barrier to agile development, that is a business model. So next, I would like to consider the relationship between technological development and business models. So this chart shows a simplified aircraft replacement scenario. The horizontal axis is the age, and the vertical axis represents the number of aircraft. So we assume that there are only two categories of aircraft in the world: wide body shown by the solid line and narrow body shown by the dashed line. Now, as a business model, we also assume a 20-year life cycle for aircraft models. For example, narrow-body aircraft with an EIS entry in service in 2020 will take 20 years to reach its maximum number of aircraft. And 20 years later, in 2040, the next generation of narrow-body aircraft will be developed. Such as, and as the number of next generation aircraft increases, number of first generation will decrease. So based on this business model, in 2050, there will be wide-body aircraft developed in 2030, and first-generation narrow-body aircraft and second-generation narrow-body aircraft. At this time, what should be the target reduction rate of fuel consumption for second-generation narrow-body aircraft to satisfy ATAG's Scenario 3 goal? So it would be 95%. I think it's almost impossible. So we found that the current business model is slow to penetrate new technologies. So this is preventing emission targets from being met through technology development. So this chart shows the results when the life cycle of an aircraft model is halved to 10 years. This shortened life cycle will help to moderate future aircraft emission targets and make them possible, feasible. Okay. So, so I would like to summarize the discussion so far. It seems that emission targets are difficult to achieve by simply replacing SAF. So therefore, it is necessary to develop technologies to reduce fuel consumption. So since hydrogen fuel is also candidate for SAF, we need to reduce fuel consumption regardless of the type of fuel. And aircraft electrification technology is a promising technology from this perspective. And the next point is that early implementation of technology is critical in the current business model. So since we cannot wait for the ultimate technology development, so agile development is important. And JAXA is considering a technology development scenario for aircraft electrification based on these summaries. So now, as the second half of my presentation, I would like to show JAXA's research and development concept. This figure shows the trend of maximum power of electric propulsion systems. Megawatt-class electric propulsion systems are becoming possible. Okay. So now let us consider which class of aircraft that the technology should be applied to. So this slide shows the trade-off between the application target and the difficulty of developing the technology. So if turboprops are the target, as shown in the previous slide, there are examples of technology demonstrations, so the technology is considered to be ready. However, turboprops account for only a small percentage of total aircraft fleet, so their contribution to the emission target will be small. So, on the other hand, if wide bodies are targeted, the contribution to emission target will be the largest, but technology development would be very difficult. So therefore, JAXA has chosen a narrow body as a target. And our aim is to expand the possibilities of electrification technology. And this chart compares ATAG, the envisioned technology application targets, with JAXA's goals. JAXA's goals shown in star, and you can see that our goal is to expand the possibilities of electrification technologies. And finally, I'd like to show JAXA's technical concept. This is the simplest configuration for aircraft electrification technology. The system consists of generator integrated into the jet engine, and converters and inverters, and the electric fan mounted in the tail section of the fuselage as BLI nacelle. And the BLI nacelle is expected to improve propulsion efficiency more than the losses associated with electrification. And our analysis shows that the entire system is expected to reduce fuel consumption by about 10%. So JAXA's goal is to complete the elemental technology demonstration of these systems by 2026. Okay, so thank you for your attention.
Thank you very much, Dr. Watanabe. I'm going to ask Ibrahim to come back up again. IFAR is giving an award every year to one of their engineers, and he will announce what that is, and maybe the rest of the panelists, if you can come up, we can start the Q&A right after that.
Okay, thank you. So just changing the order a little bit more in the interest of time. So what we do here at the at ICAS is in IFAR we ask our researchers to graduate students, actually PhD students, we ask them to submit the best or nominate the best thesis project awards, and we've got a committee here that will look after and examine the quality of them, and we select every year the top 3, and we announce the winner of the first here in this conference. So what I would like to do now next is just mention the number 2 and the number 3 selected awardees. The number 3 is Michael Momert from DLR on the topic of experimental investigation in the circulation flow and heat transport in turbulent mixed convection, which he has received the certificate, I believe, in Berlin this past June. And the second winner is Emmanuel Sunil from NLR, analyzing, the PhD thesis title here is Analyzing and Modeling Capacity for Decentralized Air Traffic Control. And the winner for this year, which is the number 1 thesis that has been selected by the committee, is from CHIRA, Mr. now Dr. Manish Nagaraja, specifically on high order layer-wise models for the progressive damage and impact analysis of composite structure. So Dr. Nagaraja is not here today. He's currently in Massachusetts, I think, University of Massachusetts. He has received the award. It has been sent to him. And he had a short message acknowledging that award. So maybe I'll let that one play briefly.
Good morning, everyone. My name is Manish Nagraj, and I'm currently a postdoctoral research associate at the University of Massachusetts Lowell in the United States. Unfortunately, I was not able to attend ICAS 2022 in person, but I have been kindly given an opportunity to share a short speech in this video. I carried out my PhD research broadly in the area of computational damage analysis of composite structures in the MUL2 lab at Politecnico di Torino, Italy. For this work, I was recently awarded the ICAS-IFAR award. It's a great honor to receive this award, and first and foremost, I would like to thank the International Council of the Aeronautical Sciences and the International Forum for Aviation Research for their positive evaluation of my work and to award me this prize. I would also like to thank the Italian Aerospace Research Center, CIRA, for their efforts in nominating me for this award. I would like to express my highest gratitude to my PhD advisors, Professor Erasmo Carrero and Professor Marco Petrolo, for their guidance throughout my PhD. I would also like to thank my colleagues in the MUL2 lab for all their support. My PhD was part of the ICONIC project and was funded by the Horizon 2020 research program. I would like to gratefully acknowledge the European Union for this funding. My research was done in collaboration with the Composites Group at the University of British Columbia, and I would like to thank Professor Reza Waziri and Professor Hannes Reiner, who is now at Deakin University in Australia, for their valuable contributions. Over the next few minutes, I would like to present a few slides to give a broad overview of my PhD work. The title of my work is The Progressive Damage and Impact Analysis of Fiber-Reinforced Composites using Higher-Order Layer-Wise Models. Fiber composites are complex material systems and exhibit multiple failure mechanisms. The complexity increases under highly dynamic loading events such as impact. Simulating such phenomena accurately requires very refined computational material models, which have a very high associated computational cost. In practice, modeling composite structures with a high fidelity resolution involves prohibitively high costs, and for this reason, coarser models are often employed, which are cost efficient but with a reduced accuracy of solution. This inaccuracy leads to the use of larger factors of safety, resulting in over-designed and heavier composite structures. The objective of my PhD research was to try to address this issue and to develop a computational approach which is both accurate and computationally efficient. This is achieved using the Carrera Unified Formulation. The Carrera Unified Formulation, or CUF in short, is a mathematical framework used to derive higher order structural theories in a generalized manner. In a nutshell, this involves the use of expansion functions within the numerical framework to enrich the kinematic approximation of the structural model. Multi-layered structures, such as composite laminates, are modeled using 2D finite elements to describe the in-plane geometry, while 1D expansion functions, based on Lagrange polynomials, describe the thickness of each composite ply. This leads to a fully layer-wise model with an accuracy approaching that of 3D finite element analysis, but with significantly reduced computational costs. And this is the main advantage of the proposed approach. In this slide, I would like to show an example of progressive damage analysis using the proposed CUF model to demonstrate their computational performance. The nonlinear material behavior was simulated using the Co2 damage model developed by the Composites Group at the University of British Columbia. The analysis considers a composite laminate with a central notch and subjected to a tensile load. The objective of the analysis is to predict the laminate tensile strength. Various scales of the laminate were analyzed, ranging in length from about 63 millimeters to about 1,000 millimeters. As seen in the figure, the tensile strength predicted by our layer-wise models are in very good agreement with experimental data, as well as numerical results based on finite element analysis. Comparing the computational cost between FEA and the proposed CUF approach, we can see that as the structural size increases, FE-based analyses require orders of magnitude more analysis time compared to CUF models. This is due to the use of higher order interpolation and expansion functions in CUF, which significantly reduces the computational size in terms of degrees of freedom without compromising on the accuracy. And this is the key advantage of the proposed approach. The layer-wise modeling approach can be extended to impact analysis as well. As an example, we consider the low-velocity impact test as shown in the figure on the left. The composite laminate is supported using a base plate and a spherical impactor impacts the top surface of the laminate. Contact algorithms, which is another capability in CUF, were used to model the interaction between the three solid bodies. The analysis predictions are shown on the right in terms of the impact force time history. Compared to experimental data, the CUF model is able to accurately capture the general features of the experimental curve and specifically is able to accurately capture the peak force. In conclusion, within this work, we were able to demonstrate the capabilities and advantages of higher order numerical models in the progressive damage analysis of composite structures. This is a topic which is largely unexplored in the available literature and constitutes the main novelty of the work. We were also able to demonstrate the capability of layer-wise CUF models in highly nonlinear problems such as low-velocity impact analysis. The advantages of this approach based on higher order models are the accuracy and significantly improved computational performance compared to standard numerical approaches based on finite element analysis. These advantages makes it a promising candidate as a numerical testing platform for the design and analysis of composite structures. This brings me to the end of a brief overview of my work. Thank you for your patience. I would be very happy to answer any questions about this research. My email ID is manish_nagraj@uml.edu. I wish you all a wonderful remainder of the conference. Thank you and have a great day.
All right, great, very good. So, yeah, please. All right, so now it's the exciting time where you get to ask some questions to our prestigious panel. There are two people running the aisles with microphones, so if you can please identify yourself when you take the microphone, tell us where you're coming from so our speakers here know who they're addressing. There's one right there, yeah. Mm-hmm.
Thank you. Hello, Murray Scott from Advanced Composite Structures Australia. Thank you for all your presentations. I'm just wondering what, maybe if you could highlight, what are the biggest challenges for the for progressing this R&D, and specifically what can IFAR do to perhaps facilitate that?
Okay. Yeah, I can probably start and you can add, obviously. I think it's a broad question, I think, Murray, and really the role of the RTOs or IFAR organizations is to, as Bruno mentioned in his slide, to provide this independent knowledge, but provide in particular information for the regulators. All of these things, as I said, has to be certified and before it goes up into flying. And one unique role that we can do is in developing and supporting the regulatory policy in accelerating the adoption. But obviously with 35,000 researchers, we can advance in these areas, in multidisciplinary areas. I think one of the areas that I think that's missing here when you do electrification or when you do sustainable aviation fuel, most of the expertise lies outside of the aviation community, and each of us can reach out to our individual ecosystems to be able to bring that multidisciplinary expertise together. That's one way of accelerating it.
Maybe if I can complete the answer. We all spoke about technology and science and so on. We must not forget the human impact and influence. I think somebody said earlier in the Congress that the whole family is lacking a certain amount of people in that, and that we need a large amount of people to be able to face all the challenges we have described. So we need to have young and dedicated and willing people working on that. I think that what is interesting in these new challenges, that there are two interesting ways to attract people to what we are doing. One is the ambition, the challenges, as I said earlier, technical research, even scientific ones. And the other one is the aim itself, the global will to find answers to better our climatic environment. This is something to be able to attract people. But clearly, we must not forget the human dimensions and the needs that we have to have those people. And to answer the second part of your question, what IFAR, and entities like us can do. You see, we have dedicated a strong part of our work to bring our peoples together, especially our young people together, in order to better know each other and be able to discuss more and exchange with each other, and then win time with that.
Okay, right. Any other questions? Yes, please. Over here, yeah.
Hello, my name is Ramon Lopez Pereira. I'm from Safran Engineering Services in Germany. So one question, we have focused a lot during the whole conference here and even all your presentations on, let's say, aviation as fixed-wing airplanes. Do you have any perspective in regards of helicopters, for instance, in terms of electrification, hydrogen power, or how would you envision also the, let's say, helicopter side of aviation, which in the end sometimes is forgotten, but it's still there, and obviously also would consume a lot of these fuels, not at the same levels as, let's say, fixed-wing aircraft, but still is a part that it's maybe a bit more complex to tackle in that sense. Thank you.
Yep. More along the lines of helicopters instead of fixed-wing aircraft.
I can give a very incomplete answer, but I didn't speak of that during my presentation. But when I was speaking about noise, you could see a strange blade of helicopter, which is the new blade for the H160 from Airbus helicopters, which is clearly a design, has been designed by the people in aerodynamics in ONERA. And this led to a very important reduction in the terms of noise. This is clearly a new generation of helicopters. I know that in the big plan which has been launched in order to solve all the problems we discussed today, there is a part involving helicopters, and Airbus helicopter is part of the efforts to be made in introducing SAFs, in introducing all kinds of technology to reduce the impact of helicopters on the climate atmosphere. But I'm not able to enter into the detail, not only due to the time, but because I don't have the details in head. But we can discuss with that if you want. I can put you in contact with people who will be more knowable than me to answer your question.
And maybe just to add from to what Bruno just said, the helicopters are not immune from this. You're right, I think they're part of the fleet, however small they are. What we see, at least in the North American context, is most of the electrification in the helicopter side is coming from the tail rotor power requirements. Now you'll see, for example, Bell in Canada and in the US are driving the tail rotor completely with an electric power. And eventually, again, using SAF and depending on the shaft power, again, the electrification, available energy density. The main rotor is also being considered. They're typically the same sort of engines that we use now for a turbo shaft versus, in the smaller scale. Pratt & Whitney Canada, for example, looking at both applications when they want to electrify their next generation PT6.
Yeah. Bruno, yeah.
Me? No? Yeah. Bruno Sainjon from Dassault Aviation. So Bruno Sainjon recalled that your organization, one of the mission of your organization is to be a bridge between academia, research, and more applied research, which is needed by industry. So my question is, as you conduct theoretical studies, experimental studies, conceptual studies also, and even flight experiments for some of you, do you take advantage of your forum, IFAR forum, to compare your policy in terms of transfer to industry? So could you comment on this? Is it different in the different countries, or is it the same kind of policy you have in terms of transfer to industry?
So ONERA versus IFAR as a general, like any changes, differences between the various organizations as to how you do your transfer?
You want to try it first? And I can go.
Thank you, Ibrahim. One thing, one starting point is the fact that should I say that the level of industry is not the same in all of our countries. And so the needs of the industry in one given country is not the same one in all the 26 countries we represent. So that's a limitation in what we do, because the role is sometimes different. But yes, we sometimes discuss about that in order to see if there are good examples which are done somewhere which can be taken elsewhere. And I must also say that between IFAR and a single organism, we have some other communities, like I mentioned earlier, area, and we also have the same kind of discussion within area, which is maybe simpler because the scale is simple, and we know that we probably all of us better know the European industry in area that in IFAR we know the worldwide industry. That's a limit within IFAR. But yes, in this field, like in all the others, with people, with technical thematics and so on, we try to exchange and be able to exchange, to make each of us learn about the best practices in its country.
Yeah. And just, again, very similar to what just Bruno said. I mean, there are differences from different countries, but don't forget the industry that we also build a bridge towards most of them are very global organizations. You know, there is Safran in Canada, there is Safran in Europe. So that helps because the global nature of the industry, the aerospace industry helps. But again, underscoring the IFAR as an organization, we're trying to merge everything together. That's not really the goal. That's actually a forum where we share the different perspectives from the different regions. You know, in North America, we may bet on now on sustainable aviation fuels, if you will, and then you'll see more on hydrogen on this side of the continent. But that actually makes it very enriching in a way. We bring back home this global perspective and differences, if you will, to each of our national organizations. So there is a huge value in sharing priorities, the different priorities from different regions. But the industry interest is very much globalized.
Yeah.
I can add that one thing I find very attractive with IFAR is the fact that it's a voluntary thing. There is no transactions of funding in any way, but people are involved because of the intrinsic value they see. And that kind of guarantee that the interactions must be useful. Otherwise, you wouldn't be in it.
Absolutely.
Yeah. Any last burning question before we thank our panel?
There's one over here. Hey.
Okay.
Yeah, good morning, everyone. I'm Luis Prado from Capgemini. I'm a chemist. So, very nice presentations. And I heard here and many other parts of the conference that hydrogen might not solve all the problems. So, how you consider alternatives such ammonia or other source of energy.
So, by the way, it's very nice to see chemists attending an aerospace conference. I mean, again, we talk about sustainable aviation fuels. We talk about hydrogen, and frankly speaking, I don't think the real experts are usually in the house when we debate on all these alternatives. So, kudos for you for attending that question. Now you're asking a fairly hard question. Hydrogen is being used, at least, the issue for aviation is the low volume density and the cryogenic nature of that in order to compress it. But in transporting it, at least what we've seen is ammonia has always been used in a way of transforming it in making it for safe transportation purposes. I'm not sure if I haven't seen any example of using ammonia as an energy carrier for extracting it again on an aircraft platform yet. But for large transportation purposes, that has been considered for sure.
Yeah. Any other points? No. Okay, so we ran a little bit over, but I thought it was good to have a few questions being asked. And we want to thank our prestigious panel. We're very appreciative of our partnership between IFAR and ICAS. And as a token of our appreciation, we have a freshly minted medallion in appreciation of all your presentations and support of our organization. So thank you very much.
Thank you.
And we will reconvene after the coffee break, and we have a great day ahead of us, okay?